in string theory, you can imagine open strings always. Open strings have two ends. Then you can imagine open strings always as connecting two planes. Essentially, when you give the boundary condition of an open string, the open string, you can give either norm or negative variable. Norm means that the open string can move. Okay? Then you can imagine this plane as the plane where the end of those open strings can move. Okay? Instead, all the set of normal variable conditions. This is all the set of normal. Okay? Then the idea is that if you quantize, okay, what I am saying now is just the connection of all what I have said till now with strings. I will spend 5 minutes on that just to give you an idea since the brain of things works. Now, then you have an open strings ending on two planes. This we call PP branes. PP branes is also in P plus 1 dimension. And this can be any string else. And the crucial point, the next point, is that if you have PP branes of the same type, the open strings that start and end on the same brane, the lowest mode is always a vector. Okay? Then if you have n of this, you should say every vector is labeled by where this open starts, let's say u, and where it ends. Okay? Not any square order. Therefore, you can think of this excitation as a matrix n by n, it's a vector. Therefore, this theory, the dynamics of this theory, is described as un. Okay? Okay, this is nice, but then let's go to our case. Our case was a 4-dimensional case here, therefore we take this 3. Okay? And this object, an, is a vector that we have till now considered. And now we want an instant. What is an instant? Sorry, by the way, I say that the vector are all the excitations of these open strings along the plane. If you want to do scalars, you can do scalars are excitation of the same open strings orthogonal to the plane. And this essentially characterize the position of this. Again, this is a matrix QV, and if you diagonalize, say all the positions of the plane in the transverse space. Then instanton, what is? This is a 4-dimensional space. We say instanton is a point of this space. Okay, therefore it's a d minus 1. D minus 1 means p plus 1 is 0, 0-dimensional. Okay. Then what are the moduli? All the moduli we did are just open string excitations, no? Open strings between what can have an open string. Either can come and go back to the d minus 1. And imagine you have k inside. You have k points. And you have open strings that start and end on the instant. Okay? And these are A, I, J, where I and J correspond 1 to K. You have K of them. And you have all possible open string connecting them. And how many they are? There are 4, no? Because you can move in any position here. This is the A, N, I, J. This was the moduli A. What about open strings starting from the d minus 1 and ending on the d3 base? Okay? This is W, something that starts in I and ends on U. Okay? W bar is the opposite way around. All these strings are oriented. It's the opposite way. Then you see all the moduli of the instant are just open strings connecting the d minus 1 and this to this. And what is the S moduli? I wrote at some point we derived by evaluating they can mix on the instanton background. This is just the action of this 3D minus 1 complexity. You just take the action. This is a supersymmetric action. Therefore, you can't just take it. We have already said that the most general action is this n equal 1 action. This is an action in 0 dimension. Okay? Both is supersymmetric. You can start from a supersymmetric action in 4 dimensions, for example. This action that we wrote, where loss, side bar, side, your action, in 4 dimensions, and you reduce to 0 dimension by simply forgetting about derivatives. Every time you see a derivative, for example, f, have a term that is dA and a term which is a. Just forget about it. If you take, what I'm just trying to say that just using the action we wrote, forgetting about derivative, you can derive this modular space action I wrote in the previous. But you see, it's a very nice picture. Everything I say here can be translated in this language, and there is lots of. But it's nice also to remember. It's easier to remember that A is a matrix. I always forget what is the size of all these ADHM matrices, but I never forget what is the size of A and W. Because for me, every time I see W, for me it's an open string between C and minus 1. And every time I see A, it's an open string between C minus 1 and B. I learned this before I learned ADHM. Once you learn this picture, you can also forget about what is interpretation in the DSU, and always use this as an effective description of it. Okay, that's all. Let's remind what we did in the last lecture. In the last lecture, we simply compute the S, right? The integral. Sorry, the integral of e to the s, we consider theory n equal 1 super QCD, was a theory with S range H2 and NF fundamentals and NF anti-fundamental. And we noticed that in the background of an instanton, this theory contains a term that looks like lambda to the integral T for x, T2, theta 0. And then here you find W of Q tilde. Okay? And this W was a function that was completely generated from the instanton and was looks like this. Phi tilde was lambda to the 2n plus 1 divided by the determinant of phi f phi z f u phi f f1. Because this was 2n plus 1. Okay? What we realize, what we see is that you take, this was integral of all the fields of the Seiberg means, and this integral reduced to an integral where the modular space of E minus S moduli. And these were just, we first realized that just from dimensional analysis, only k equal to 1 instanton can contribute. And only if NF is equal to NF. For this particular class of gauge series, the instanton generate a highly non-trivial term, non-perturbative superpotential, which is of this form, and will be always of this form, you see, because fermions couple always to phi bar. Okay? But this should be homomorphic. Therefore, the boson should always come with a determinant in the denominator, producing phi bar, cancel the phi bar, and then this will be always of this form. No? It will be some lambda dividing some determinant, some holomorphic. Therefore, this is a holomorphic function in the fields. Okay? And it's very special in the sense that it's not what you typically are used. So you're typically used to polynomial like interactions like Yukawas and so on. This is a very strange interaction generated. Therefore, you can imagine that the effect on this will be completely different from all what you have, all what you have seen before. Okay, this was what we say for n equal 1. And then we start to look to n equal to 2. And in n equal to 2, we say that the interesting object to study is the prepotential. It's again a holomorphic function. This was the superpotential. In n equal to, what we should look for is the prepotential, which is a function of the superfields. Okay, in n equal to, you can have vectors and hypermorphisms. The vectors, remember, contain one scalar field, and the hyper contain two scalar fields. Because remember, the hyper were two chirals, and the vector was a vector plus a chiral. For they have one complex field, and the hyper have two complex. Then you can now consider now you can consider here two branches. No, you can consider a branch in which this is different from 0, and this is called Coulomb branch. Or you can consider a branch where some of these guys are different from 0. And this is what is called Higgs. Okay? From the point of view of non-perturbative effects, this is the interesting branch because this is together with the vector. And the vector is the one that we have a non-trivial configuration, the instanton. Therefore, we will focus on this branch. Every time, I will put always the depth of the hypermultiplets. When I include hypers in my picture, I will always put the depth to 0. I will always talk about the Coulomb branch. You can see that the Higgs branch is not renormalized, it's exact the answer. There is no corrections. Therefore, it's less interesting from this point of view. Okay. Okay, then what we want to, okay, then this vector multiplet together with the vector, this scalar together with the vector, you can construct, I said that in n equal 2 you can really construct a superfield. Let me write here. Which starts like phi x. It's a big superfield, it's bigger than the one of n equal 1. Then you have the lambda alpha, theta alpha, then you have FMN theta, theta plus so. Okay, it's a big stuff. And the nice thing is that you can write the action of n equal 2 in terms of this as d for x, d for theta, remember d for theta are all thetas, not theta bar, of this big prepotent. Holomorphic, this f of phi is a holomorphic function, which is what I call prepotential. This is the prepotential. For example, the simplest case is just take f of phi is equal to phi squared. It's the trace of phi squared. Okay, if you take that, let's see what is this. Integral s of n equal to integral d for x d for theta of trace of phi squared. What is that? I can take, for example, the 4 thetas from here. Before I have now numbers and so on, you have the integral d for x trace of f to the 4 f squared. This coming from here. And then you can see also lambda with here there will be the limit of lambda, you will find the lambda di lambda and so on. Okay? But I don't need to show you this. I just need to know that everything can be written in this form. Therefore, if I compute this function, exactly all the corrections to verify from the instanton, I know it's the full action. I can then just plug, take this superfield, so that I take from some text, plug there and just keep the tick to the 4 component, and this is the action. Okay? Then what we will do now is compute this. Okay. Okay, and then how we compute that? We say that the main point is again to compute this modular space integral. The essential object that we will compute, let's call set, is the integral over the modular space of k instanton, okay, for the group SUN of the exponential to the S of moduli. Where S moduli will be again some polynomial function of omega, A, Fermions, and so on. Okay? This is the object there. And we have seen, well, the idea is to compute this object with this localization formula. We simply say that if I have an equivariant charge such that Q of, and I have a form which is closed under that, okay, where I psi is an action associated, I don't know, it's an action associated to acting on my manifold. This is psi, some action on my manifold. This manifold has to do this. Okay. And it's an action with isolated fixed point. This is the crucial one. An action with isolated fixed point, then the integral of alpha is equal to the sum for the fixed points of alpha 0 evaluated at the 0 fixed point divided by the Q squared. And Q squared is just the action. Q squared I Q is I. And CI is simply defining how my fields act on the CI simply say in which direction I move every point. From the left here on this, and this moves me to this. This is how is that?
Sorry, can I? So basically, we are trying to calculate the prepotential just because we are in a regime where the instanton contribution is the main one.
Yes.
So we know that the action will be localized on the instanton background, and yes, from that we calculate back the prepotential.
Yes, yes. The prepotential is again the effective function. You remember, every time I compute this integral will contain always a term with d4x, which is the zero mode of the instanton here. Will contain a term with d4 theta, which is coming from m alpha a. That now a is going from 1 to 2. Okay? Therefore, this integral here contains already something times whatever it is, all the rest I will call prepotential.
Okay.
Therefore, what I will compute is this integral here, and from this integral we know that this is exactly the prepotential term. Okay? Okay, then we know already what is my manifold. My manifold is this manifold, the modular space. We should say what is the symmetry of this manifold. What are those U-bars? What are the symmetries here? Okay, here we have a symmetry which is UN. We have a symmetry which rotates the K index, which is UK. And we have the Lorentz symmetry, SO4. By the way, notice these are the gauge symmetries of the instant. UK is the gauge symmetry of the D-1, UN is the gauge symmetry of the DC, and okay, SO4. Okay? Therefore, what I should do, I want to review one, no? Therefore I should break this integral. You see, this is the main point. Why we were not able to do this integral is because this integral have a lot of symmetry, have a lot of flat directions. This is like a potential, which is, this do not have meaning. You see, this isolated points means that you have a potential. Fixed points, isolated fixed point means that you have vacuums, which are isolated. But this is not our case. Because we have a symmetry UN. Therefore, any vacuum is related by UN to another vacuum. Or to UK and so on. Okay? Therefore, this action will not have fixed point unless I break this symmetry. Okay? Then what I will do is I will break this symmetry. I will introduce parameters in such a way that UN I break to U1 to the N, UK I break to U1 to the K, and this I break to U1 to the K. How I do that? I simply turn the vacuum expectation values in the Cartan of this group. I take some parameters. I qualify this any element of UN by the Cartan parameters, the parameters in the Cartan. Let's say I take AU, sorry, this AU have nothing to do with this A, Chi, I, and let's call X1, X2. This is just the Cartan of UN, the Cartan element of UK, and this is the Cartan of SO. Okay? Essentially, what I'm just saying is that if you have a matrix n by n, you can always diagonalize. And the eigenvalues I call AU, and 1 and 2 till AN. Therefore, this U goes to 1 to n. Okay, maybe I expected to call it I here. I is 1 to k. And epsilon L, L goes to epsilon L. Okay, this part, right, this one is not a big deal because breaking UN, you could interpret this phi as we say that we want to give we want to start in the theory in presence of vacuum expectation value for the scalar in the vector matrix. Okay, the scalar in the vector matrix is a matrix n by n. It's a matrix n by n. And now what we are saying is that we will write in this form. Just like this is the wave of the scale. This is the way to break UN. Okay? You instead of consider a gauge theory in an arbitrary, I mean, this you see always with a gauge symmetry you can always diagonalize. Fine. Therefore, this is not, you're not losing anything doing this. Then, okay, the UK is the same. We will introduce a field in the instanton model space chi, which is diagonal chi1 to chi k 0, which simply parameterize these UKs. This is just a way of parameterize this, how all these UK rotations. But this is a big danger, because this will break Lorentz invariance. But we want a term which is Lorentz invariance. We want a prepotential. We are in a theory which is Lorentz invariance. Okay? And this was the crucial point. This was the missing point why localization was not never applied to this type of thing, because really the point were not isolated. What was realized by Megas at the time was that you can introduce these parameters. At this point, the fixed points are isolated. You can compute using localization, and then send this parameter to zero. The Lorentz invariant will be recovered at the end, just sending these two parameters to zero. Okay? Okay, now let's go ahead. And now it's very simple. We should compute the Q. We should write what is Q. Q, we say already that is the supersymmetric charge. We will take all our fields in the instanton model space, and we will make a big table. Right? What are the eigenvalues respect to Q squared? Okay? And compute the determinant. you reduce the full computation of this integral, which is an integral 4 kn dimensional, to compute this determinant. By the way, yes, by the way, the fields are rotated by all the fields of the instanton moduli space are rotated by this symmetries. For example, W was UI. This means it's a fundamental of UN, a fundamental and fundamental of UK. N was IJ. It was fundamental of UK. And this has alpha dot. This means this transform to Lorentz and so on. And you are rotating with this symbol. Then what are the fixed points? Just the origin. You're rotating. The only fixed point is that you take all these fields to C. This is the only fixed point. Therefore, we are in the condition we want. We have a condition in which we have one fixed point. Okay? And this is nice because what was this alpha 0? This alpha 0 was S moduli evaluated at the fixed point. But this was polynomial in your fields. Therefore, this is 1. The full integral is just a determinant. Like we make a table, write all the eigenvalues, compute the eigenvalues, and we finish. Okay, let's do the table. By the way, in this picture, if you want to understand, AU is the position of these D3 branes. Chi I are the position of the D minus 1. And you can imagine you can distribute this phi n. This break UN to U1 to the n, because now you have U1 every time. And then the instanton sum of them will be here, 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 and so on. This will be the chi1, chi2, chi3. This will be A1, A2, A3 in this line. Okay? Therefore, yes.
Sir, this point, the origin was a fixed point also for the old symmetry, not just the broken one, right?
Yeah.
But this point was not isolated, so there were.
No, the point is that if you don't act with this U1, if you don't follow these parameters, you have really not a U1, you have an SO4.
Yeah, which still has a fixed point, so it isn't.
Yeah, but it's SO4. This fixed point A is just with U1s.
Okay.
This is very more difficult.
Okay.
Okay, let's do the table.
But Francisco, it's not clear to me that you're not missing. So, what are you missing by breaking to the U1?
You will find an answer that depends on x01 and x02. What is that? We will find now a prepotential. We will find a prepotential that is a function also of x01 and x02. Okay, x01 and x02 are a rotation inside Lorentz. This means that our answer will be not invariant. By the way, this answer is very interesting. Also for x01 and x02, now we realize that these two parameters are really very important, are very nice and so on. But from the gauge theory point of view, they are very bad because they break Lorentz. From the string theory point of view, they are very interesting. If you expand in x01 and x02, you find all the topological amplitudes people found in the past. And there are a lot of applications of this x01 and x02. For example, you can interpret in connection with CFT, you can interpret this x01 and x02 like the central charge of dual CFT. I mean, now there are a lot of words computing this prepotential at the dependence from x01 and x02. But at the beginning, the idea was that we want a Lorentz invariant stuff, social invariant on the SO4. Therefore, we should send these parameters to 0. Okay? We want a prepotential that depends only on the depth.
No, but my problem is not that. My problem is what do you miss from the larger group?
Sorry. We want a prepotential that depends on A. Chi is not a problem because chi is a symmetry. It's a gauge symmetry. Therefore, I should integrate over chi. Okay? But if I would keep x01 and x02, I would find that. Then I say AU I can interpret as the depth of phi, and it's okay that my prepotential depends on the depth I put for my field. But what I do with x1 is going to. And the point with the fixed point, I say that if you have a symmetry, any fixed point you find, you can move by the symmetry. Will never be isolated. Then you will not have sum. Of course, you can do an integral and things like that. But for sure, this will not be sum over the fixed point. Now you could do something more sophisticated, integrated over a fixed point.
Could you repeat this once more? So if you have a fixed point, how can you move it by the symmetry if it's a fixed point? Sorry, I know that it's probably very stupid, but I'm just not getting it.
Sorry, say again.
You're saying if I have a symmetry, I have a fixed point, I can move it, so it's a line of fixed point. But I'm not getting it because if it's a fixed point, how can you move it by the symmetry?
No, I'm just saying that you will have a line that any point in this line will move. It's a line of fixed points. Every point is fixed, but it's a line. It's not isolated. I say that the localization theory, one of the hypotheses, that the fixed points are isolated. Means that you cannot have two fixed points very close to each other.
So you're saying this action, besides the fixed point at the origin, has a line of fixed points somewhere.
Okay. Then let's do the thing. Now what I will do here is I take all my fields and group according with the same quantum number and group according to supersymmetry.
There you are outside of the camera.
Sorry?
You are not in the camera if you write them.
I am not in there.
In the camera.
No, you are, don't worry.
That's your.
No, it's in the camera. It's in the camera.
Did you understand yesterday what you should make the shot? You know.
That's because we got
Okay, let's do here. I take all my fields. For example, what were my fields? A, alpha, dot. Okay? What is the pattern A alpha dot was the matrix A by K? Okay? What is the pattern? Oh, okay, this we already see. We already see that we have this supersymmetric transformation that say that variation of delta was n, but delta was omega A, and n was it's B. And n was mu n alpha. Okay? Therefore, the partner of A was n. So this is the supersymmetry alpha A. And I have two of them. I have two of them. Let me call from now on this index that label the asymmetry. I will call alpha dot. In such a way that the supersymmetry relate fields with the same. This is Q. No? What we will organize all my fields now. We organize as variation of a boson is equal to n. Or let's say Q acting on a boson. This will be my Q. Okay? While Q squared, Q acting on a Fermion, which is the same as Q squared acting on a boson, is okay. This will be the symmetry. ADHM. Okay, I take now all my fields. Remember, the supersymmetry charge will take always a field to another field of the different spin statistics. For example, we'll take a boson to a Fermions. And if I do Q squared, we know that Q squared is just a variation. Therefore, this is a sort of deformation. We call it equivalence because it's a sort of, you would expect Q squared is equal to 0. We are saying, okay, Q squared is not 0, but it's a symmetry. Therefore, if you act on something which is symmetric, this is like 0. No? Every time you act with this Q squared on something which is symmetric, this is 0. For the simplest generalization, you can do via T charge. This is not a BST charge, but it's almost a BST charge. For a physicist, this is a BST charge. Because we will always act on an action which is symmetric on objects that are symmetric. Okay? Okay? Then let me call this lambda. The eigenvalue of phi with respect to this action, let me call lambda. Remember, all my actions, UN actions, UK action, and SR4 actions are already diagonal. I choose, for simplicity, all my action diagonal. A1 into A, Chi1, Chi2. Therefore, the action of all the operator is just an eigenvalue. I have a field, and I know how they act. Okay? Therefore, next time, we make a table that say this. Here I put the origin, and where it comes. Here I put the two fields. Then I will say, I come to this point now. The representation with respect to UK UN, the representation with respect to SU2 squared, and the eigenvalue. These two have the same information as lambda. Because lambda is simply the eigenvalue with respect to this action. Okay? Now, for example, let's consider the gauge part. Gauge part means all the moduli that come from the gauge condition. What are the fields? We say, okay, one of them is A alpha dot, N alpha dot. There was 2N. This index I call alpha dot, therefore you see they have the same. And we check explicitly that there was this thing. There was this delta of A delta of omega A was equal to mu n. Now what we are doing is we are adding, since we are in N equal to 2, we have this index A here. Okay? And this index A we call alpha dot. Okay? Therefore, you see that you have completely similar. The variation of W will be mu, variation of A will be N. This we have proof. Okay. Now, what is minus 1 to the F? It's just the spin statistic of the lower component. This plus. Why I say that? Because we have, okay, let's go for the moment, it's always plus. We will find some multiplet that start with a Fermion. We later come to this. But for the moment, let's forget about this. UK, UN, this transform like KK bar. No, this is K by K matrices. No transformation. Lorentz, alpha go from 1 to 2, alpha dot from 1 to 2. This is 2, 2. Alpha, these two Lorentz, this is SU2 alpha, and this is SU2 alpha dot. You can imagine this alpha like the components, let's say this is plus plus minus minus, and this is plus minus minus, for example. Okay, this is the two spin. Let's move on right. Okay, these are the possible entities. Okay. Then what is lambda? Okay. Then lambda, I just read from here. This is a matrix IJ. Okay. Therefore, this will transform under a small transformation of UK. This will transform like chi minus chi j. No, you have chi is index. This is I bar, k bar. One transform with plus, the other with minus. So these are just U1s. Okay, one is fundamental, the other is anti-fundamental. For this one is chi minus chi j. And then you have alpha dot. Therefore, here you have all possible combinations. Okay? Then alpha, for example, the first one will be plus epsilon 1 half minus epsilon 2 half. This will be, let's say, one of the components of the, this is plus minus. These are the two components of the alpha, and these are the two components of the.
Excuse me. This is the eigenvalue with respect to Q square.
With respect to Q square.
Okay.
In Q square, I just put all the U1s in. What is that? Okay, let's see. Let's enumerate here. You will find, for example, here you will find epsilon 1. You will find epsilon 2. You see, epsilon 1 is plus. When you take both plus, keep only epsilon 1. The other keep on saying 0, 2, and then you find the two sides. Okay? But this is a complex field. I will always write the value of this is a complex field. You will always have plus and minus. Therefore, I will always write the plus 1. Okay? Therefore, here, I will always work with this complex field. Therefore, my determinant to 1/2 is simply determinant. We write here determinant, and I will just enumerate the plus 1. We know that every field, every complex field has always the complex agent. Therefore, what I have here is chi, let me call this chi ij, plus epsilon 1, or chi ij plus. Two eigenvalues, because are 4 reals. 4 reals is 2 complex, 2 different eigenvalues. One is epsilon 1, chi ij plus epsilon 1, the other is chi ij plus epsilon 1. Okay? Now, what is the next? The next is this W. W alpha dot, mu alpha dot is, again, plus. Now this will be Kn, Kn bar. Okay? This is respect to Lorentz is 0, 2. Sorry, 0. It's a singlet. Is a singlet respect to alpha, but transform as a doublet respect to alpha dot. Therefore, this is what? This is chi I, chi I minus AU, because now it's n bar. And here you will have plus 1/2 epsilon 1 minus epsilon 2.
Why was it K bar?
The first one.
Yeah.
Because this is K bar. This is a math.
So
this
how does it transform for under UN?
One fundamental and the other is anti-fundamental. The first index, this was a matrix. Every time you see a matrix K by K, you should imagine this matrix as something. The first index in the K and the second index in the K. The joint of UN is n times n bar. Sorry, K times K. Sometimes you write the matrix as one index up and one index down, and then for you the up is bar and the other is down.
But is, I guess the question is it trivial? Does it transform trivially under UN instead? That is KK bar, which is under UK.
UK. It's trivial under UK. Yes. Yeah, it's trivial under UK. If you would like to write like this, you would write this. And this you would write like this. If you want to see the two. Sorry. Okay, this is W. You have also W bar. Sorry. Which is just a complex conjugate of this for BK bar n. And this will be 1, 2. And then again here you have AU minus KR, IR plus 1. Okay? And then what was missing? Okay, what was missing was the ADHM constraint. Okay? The ADHM constraint, DC, remember, is something like just subtract. Okay? Then better associate to this effect. Then you have DC, okay? DC is a degrees of freedom I should subtract. Therefore, what I will take is I have, so let's see what are the degrees of what I have. I have the DC that was, you remember, omega bar tau C omega plus eta C mn commutator AMN equal to 0. We have this constraint, and we have also a fermionic constraint, and now we have A that was something like mu A omega bar alpha dot. So, okay. Now what I do is I take the constraint. We already showed you that this constraint was related by supersymmetry. Therefore, this is a model. Okay. Of course, this cannot be completely true because these are 4 and these are 3. But okay, let's say 3 of these guys are the part of that. And the identity part of that, then therefore let me write this lambda multiplied by tau C. At A, I say that it's like beta dot. Okay, A goes from 1 to 2. Therefore, these are 4 lambdas. Let me split this 4 lambda in something I call lambda G. These are 3 of them. And then the last one, how I want to call okay, and what we know is that lambda C and DC are parallel coefficient. Therefore, we have lambda C and DC. And why I put in this order? Because I want to subtract this degrees of freedom. If I would write here DC, this will come in the determinant, this will add degrees of freedom. This is really therefore what the idea is that you can always think of constraints as a fermion degrees of freedom. A constraint is something you should subtract instead of.
It's a Gauss in some sense.
It's like you could imagine like writing as the integral of Gaussian.
So it's Brown spin statistics.
Okay, but the important point is that every time you have a field, you put plus here. Every time you have a constraint, you put the fermion first. Then these have opposite statistics. Therefore, you have your determinant, and all the fields contribute in the denominators, all the constraints contribute in the numerators. And how these transform? They transform like K bar. They were K by K matrices. DC, what is DC? DC, remember, DC was delta, was tau C, alpha dot, beta dot. Therefore, this transform like only in the alpha dot, beta dot, like twice this guy. Therefore, this transform as the 3, 1, 3 of the alpha dot. Okay? It's antisymmetric. You see, this transform like sigma mn. This transform as a self-dual tensor of Lorentz symmetry. In fact, the self-dual tensor is okay. And what are the J values? Again, chi are J, because it's chi bar. And then this is 3 means 2 of this guy. Therefore, you have plus minus epsilon 1, epsilon 1 plus epsilon 2 over 2 plus minus epsilon 1 plus epsilon 2. Okay, then what are the combinations? Here I have a combination that gives the sum of the 2, which is gives epsilon. Let me call epsilon from now on. I will call epsilon 2, epsilon 1 plus epsilon 2. Okay? Therefore, this will be chi 1 plus chi 2 epsilon. This is when they have the same sign. And then you will have something that is chi ij. And notice, this is very strange stuff. This 3 instead of 4 is not complex. But we should remember that we have also the eta. No, I mean, this makes no sense. This is 3, but we have still the eta. Then what we can do is just introduce an extra field, I will call chi bar. You see, every time I have a field missing in my supersymmetry, I add. You remember, we did this with the superfields. You have your fields, there are more degrees of freedom for Fermionic composition, you add one. I add this auxiliary field, in such a way that I cancel these three. You see, this, I will give the same, now this is plus, calculate bound. This is a Lorentz, this is a singlet, and what I want is to have a value character. In such a way that this and this I cancel. Otherwise, I'm a bit trouble because this is, by the way, notice that this have even eigenvalues that are 0. Because if I is equal to j, this is 0. But fortunately, I cancel it. Otherwise, in this determinant, I will have a 0 somewhere. Okay. That's all, we finish. What happens if I put fundamentals? If I put fundamental, I have this K. And again, I don't have the boson for that. Therefore, I add some boson, I will call H. This is now a fermion, it's minus. And here is, this was what? This was in the fundamental. Okay? Okay, but then I should add a new, let's say UNF. If I have some flavors, I have also the flavor symmetry. And again, I should introduce a parameter for this flavor symmetry that I will call mass, NF. This is just a parameter that qualifies the cartan that diagonalizes this UNF. Therefore, now this will be K times 1 times NF in the fundamental. This will be, sorry, in the fundamental and in the anti-fundamental of NF. Okay? Will be a Lorentz singlet. And the eigenvalue will be Chi minus MF plus this. And the same if I have anti-fundamental, I have K tilde H, I have minus, and this will be K bar, 1 NF, 1 and this will be Chi MF minus. Okay, now this is the formula we will use. Let's compute. A partition function of order k will be equal to that, according to this formula. The partition function was the integral of alpha. We say that alpha was exponential to a minus s mod. This is supersymmetric. Say that was supersymmetric, then automatically is invariant on the T. Okay? Therefore, it's equivariant by construction. By the way, notice that all what I'm doing, you can do in any supersymmetric theory. This is the power. This formula is just saying that if you have a supersymmetric theory, the integral of the action is just the action evaluated at the minimum plus the fluctuations around the minimum. This is completely general. Okay? The only thing that you should be careful is to define very well this determinant in such a way that you can compute it. If you have a strict form which is isolated, you can compute very well this determinant.
Is this completely unrelated with the beta function?
No, it's exactly that. Because you see, this determinant, I could write like exponential to the trace of log. And this is exactly the one loop correction. So you have boson and fermion, this would be a log determinant of the d squared for the boson and d for the fermion. So it's exactly the one loop. You can imagine this as the one loop.
So was the vanishing on the beta function at higher order proved before localization or with?
But well, two different things. One is the correction to the beta function. Now what I'm saying is the correction to the path integral, to the full path integral.
Yeah, so that's why I was asking if they were related or not.
They are related in the sense that both are one loop corrections. But they are one loop correction to different quantities.
So not
But I'm saying that every time you have one loop correction, you can interpret it in this way. But is it always a different quantity you are computing? Okay. Now, let's write now the general formula, set k. What we are saying was that the integral over the modular space and k e to the minus s mod k will be will be the integral. Okay, still I should project on the gauge C. Therefore, you still should integrate over chi and divide by the volume of k. This was the gauge symmetry of the instanton modular space. Okay? And then you should compute this determinant. This determinant is just the product over all the fields you have in the theory of lambda phi, the J value of that field to the minus 1. Okay? Now, a matrix this matrix chi, we say that we can diagonalize. Therefore, you can diagonalize that in terms of, you can write this integral as d chi I. Okay, therefore this is product from I to 1 to k d chi I. Okay? But you have a Jacobian. No, of this transformation, the Jacobian from going from chi to chi I. And the Jacobian of this transformation is what is called van der Waals determinant, which is product if I different from j of chi I j. Chi I j. You can see this, no, because these have k squared terms. These have just k. You need k squared minus k, and you need that this is H invariant. H invariant means symmetric on any interpretation and just a difference. This is the only thing that you can do. Okay? Otherwise, you can just do the change of variable and see this is the Jacobian. But this is the only variant with the high dimension. What you do. And then you should do this product. Now let's see what is this product. Let's start. Let's start, for example, from all the fields, this A, for example. Product, this A will be product on I and J. Okay, going always from 1 to k. So this product goes from 1 to k. Of what? Chi ij, this is with plus. Therefore, in the denominator, I will find chi ij plus epsilon 1 and chi ij plus epsilon. This is the A. Okay. Then you have also this one. This is also k by k. Okay. So here was just plus x. Here was just plus x. Then the minus is in the other. I'm just writing one of them. There is only one value. Then from the d, you remember these were originally were 3, but one of them was already cancelled. Therefore, there is only one context, and give chi ij plus. Okay? Then I have product over I from 1 to k again, and product over u, okay, of 1 over product over u from 1 to n. Now this is the contribution of w that gives chi I minus au plus epsilon 1. Sorry, there was a clause here. This was alpha dot. The index alpha dot in our notation is epsilon 1 plus epsilon 2. So this is plus epsilon over 2 Okay, I can cancel this already, no? This formula we already used before. Okay, and for the bar, the same things. AU minus chi I plus this. Okay, I finish this part, then I have just this one. If I have fermions in the fundamental, I will have also product from F is equal to 1 to the number of fundamentals of chi I minus MF. And then if I have anti-fundamentals, I will have product the number of anti-fundamentals MF. Okay. Sorry, I forgot here in this Jacobian there is a 1 over k factorial that simply say that all the chi I are equivalent. Okay, chi I are the eigenvalues of a matrix. When you analyze a matrix, you don't care about you put the first eigenvalue in the first position, the second one. You can permutate all the eigenvalues. This is this one. Okay. That's all. We finish. Then this is set k. Okay. Now, what we will do now? What time is? Okay, good. What we will do now? Okay, then what is the partition function? The partition function is sum over k, set k, qk. Okay. Now, what we would like to do is the limit of this partition function when epsilon 1 and epsilon 2 goes to 0. This is what we will do. We now recompute this stuff, and we will take the limit at the end, which will take these epsilons to 0. Okay? Let me anticipate what we will find, and we will verify explicitly in some computation. There is no any obvious way to see it directly. What we will find is that this quantity here, when I send epsilon to 0, diverges. And diverges very badly, in this way, exponential to minus epsilon 1, epsilon 2. Okay? Times some function, let me call it. But this is not so bad, because this stuff here is roughly the volume of the space. What we are doing really is we start from R4. You see, we start from R4, but I have fallen infinity. We turn these parameters, epsilon 1, epsilon 2, they deform the R4. What is happening is that this space becomes compact. And if you compute the volume of this new space with this deformation, you will see that the volume goes like 1 over epsilon 1, epsilon 2. Then when you send epsilon 1 to 0, the volume is to infinity. Therefore, you can imagine this like p for x t to theta. By the way, notice that have the right dimension, no? No. Yes. D for x, d for theta. Because it's n equal to 2. Then this has dimension 4. Minus 2 is 2, which is exactly. So what I'm just trying to say, this you should buy. Listen. But if you compute the volume of this space, this is roughly the volume. Therefore, what we do is we interpret. For the moment, you can see in this way. You see that this function is not infinite, it goes to infinity, but it goes to infinity in this way. Exponential of this times something finite. Okay? And this is what we will identify with the prepotential. In the beginning, people don't know anything of this. They simply notice that this goes to infinity. They say, what is this function there? They compare with other computations. Well, already from the prepotential, it's the only function we know, and they see that this much. It was a miraculous outcome.
This compact space has something to do with the torus because it has a 1 times 1 symmetry, or it's not.
So it's
the compact space you get.
It's not a torus. It's not a torus.
but it has a U1
They
tensor.
call R epsilon 1, epsilon 2. R4, epsilon 1, it's not a torus. But have a volume, have a final volume like a torus. It's compact like the torus, but have not. For example, do not have one cycles. The torus have trivial, non-trivial one cycle. This is not the case. Okay, but for you, okay, just simply say this goes to infinity, and we will see that although set goes to infinity, f, which is minus epsilon 1, epsilon 2 log of set, this is fine. Then this is the quantity, the interesting quantity you can extract from here. It's minus epsilon 1, a limit of when epsilon L goes to infinity to 0. Then we will define the prepotential by this. For the moment, this is just a prescription. Okay? But you can compare them later with a different computation of the prepotential and see. For example, you can compute the explicit k equal to 1 and check if this gives the estimates. Therefore, now what we will do is we take one simple example. We will compute this set, compute the log, and compute the first few terms in this okay, for like, I don't know, SU2. Is there any question? Okay, maybe I can say already something still general. Let's look to this integral. Okay, this integral, I am integrating all these chi are integral by minus infinity to infinity. But this is very bad because this has we have a lot of poles along the line. How I solve this, I will give small imaginary part to all of this. Therefore, I take imaginary epsilon 1 is bigger than imaginary epsilon 2, is bigger than imaginary of n, bigger than c. Okay? Once I do that, it's much bigger if you want. In order to, there will never come, there will not be cancellations. Therefore, once you do that, you see all the poles are away from the line. Okay? And then at the end, I will send this imaginary part to C, of course. Okay, okay. But then this is nice because now you can now close. You see, if this goes to 0 at infinity, we are doing integral over chi, chi1. Okay, and we have some poles here. Okay. Now imagine that you don't have matter or you have few matters. Therefore, this goes to 0 at infinity. This is the same number. You see, here you have k squared. Here you have k squared. Therefore, here it's more or less the same number. Here, if you don't have this, this is at infinity. At infinity, this goes to 0. Therefore, if you have few matters, the theory is asymptotically free. This, let's take pure derivatives if you want. All this goes to 0. Therefore, I can close the contour and evaluate this integral by simply computing the residues in this place. See, we reduce the full computation of the very high end just to computing residues in few points that we will have poles. Okay. Now, let's see also how they lose these poles. You see, for example, imagine you take I1. I mean, you can start from all the chi are equivalent. There is k. You can calculate. Let's say you start with chi1 and put chi1 is equal to a. You take one pole from here. Sorry, it should be positive. Therefore, I should take this one. No, it should be the post should be a positive real. Therefore, I take this here. It's a equals epsilon. But then you can also take from here, no? And here what happened is that in order to have a pole, you should have two chi's that differ by epsilon 1. Okay? Therefore, essentially, the picture is there to follow. You start from chi1 at one point, and then you can take the chi2, you can take either at the distance epsilon 1 or at the distance epsilon 2. And then you have k of them, then you can build them. Don't know. Always separate at the distance. Then what you get is a J tableau. What you can prove, now I'm just giving some heuristic argument, but you can prove this, and we will see explicitly in our computations, that the poles here are in one-to-one correspondence with J tableau. Sorry, how many J tableau? You have n size. Therefore, this was N1, this was N2, N3. Therefore, you can also put some instanton here. Here there will be another J tableau. Example. Here there will be another. Therefore, if you are in SUN, you have n J tableaus. Therefore, the statement is that there is a one-to-one correspondence between the poles of this. It's a mathematical statement. I just look to that and see where are the poles. By the way, it's not even true, but you can see that all the poles that are not of this type do not give contribution. Or cancel between them. Or there are also other poles that have eigenvalue 0 and then they cancel. All the relevant one. What you can see already is that a J tableau is for sure a pole of that. This you already see, because it's always 0 here. If I have this is chi1, chi2, chi3, chi4, I see already that these are 4 zeros. One from here, one from 1, 2, 1, 3, 1, 4. And this is 1. Therefore, we already see that this is a pole. Now, why these are the only one is a little bit more subtle, but let's believe it. Okay, therefore, this is very nice. Then, if I want to compute an instanton contribution, what I should do to compute set is I should sum over all possible sets of J tableaus, okay, of this set, where this set is the residue of this quantity we call set K. Let me call this quantity I already called set K that, small set K. Okay, residue of set K in the pole chi I is equal to this stuff. Let me write chi I. Now, this index I was K index. I will write in this form. This chi I is labeled by by U I J. Well, this is just saying, let me call I the position of every box of the tableau is an instant. This is I is equal to. Let me call. This is was I1, no? This box I will call 1, 0, 0. This is the U, I, J. This is U is 1, and this is the 1, 1. The first line and the first column. This will be U is equal to 1, I is equal to 1, I is equal to 2, J is equal to 1, and so on. Right? Then what I'm just saying here, the position given a J tableau, I know what is the position of this. The J tableau, I read the position of each instanton by simply taking, for example, this one was A3 plus 2 epsilon. Sorry, this was 0, epsilon 2, 2 epsilon 2, and so on. And this is the same. This is epsilon 1 plus epsilon 2. Therefore, I asked yourself, what is the J value associated to this box? Is A3 plus epsilon 1 plus epsilon 2. What is the J value associated to this box? Is A1 plus 2 epsilon 1, and so on. Therefore, the Young tableau say you already where the instantons are, or where the poles are. Okay? Another way of doing this computation, you put the mathematics and compute the rest of all this and you get the answer. I'm just saying that this is nice because then you can extract a lot of properties without this computation. Of course, at some point will become complicated. No? But now we'll see even that you can even resolve the full series sometimes. I mean, you can do a lot of things if you know the general structure. Okay. Then let's do one case because otherwise everything looks too vast. Now I can cancel this.
Sorry, what changes if there is a lot of matter instead?
Is there a lot
If
of?
there is a lot of matter, so that the integral doesn't go down to infinity.
In principle, it's not justified that you can do that, but you find the right answer.
Okay.
Till conformal. Till conformal, you can do. Conformal is exactly when this exactly cancels out.
Okay.
Then I don't know why you get the right answer.
Okay.
It could be that in this case there is an ambiguity in the answer. When I say I get the right answer, that means I get for a given. You know, conformal theories are a bit softer.
Can I ask a question?
Yes, please.
Just a curiosity. Young tableaus classify the reducible representations of SUN?
SUK.
SUK.
No, because you see there are n of them. A Young tableau. A Young tableau has classified the reducible representations of, you would say UK, but you have n of them.
Yes.
You have n Young tableau. Therefore, it's also that depend on n and k. I don't know what it is.
So is there an action of SUK on the set of poles or something?
SO4.
No, of SUN on the set of poles or something similar? Like, why do they call
The action in SUN is simple, no? This A1, A2, A3 were the eigenvalues of SUN.
Yes.
The action is simply the permutation. Okay? In SUN. And in SUK, then this is like you are decomposing the UK factorial in UK1. Let's say with 3 on top of UK2, UK3. And now you're right. This is like a visual representation of the UK1. Okay, the good question to you, the good answer is the following. You have your D3 planes, the split of them, you put some K1 instanton in the first, K2 instanton in the second, K3 in the other one, and these are classified by the reducible representation of this UK1, UK3. And all possible reducible representation of this UK1 will give something. Okay. Okay, then let's do n equal to 2, k equal to 1. Sorry, n equal to 2, and then let's start with k equal to 1, k equal to 2, and so on. Let's do the pure case. Okay, the case with fundamental is the same. You just change the values. Okay, what are the contributions? Let's say k equal to 1. Okay, k equal to 1 means I have a single box. Okay, I have all these slots, A1, A2, A3, AN, and I decide to put the box somewhere. It's called AU. At the position U, I put a box, one box. Okay? Then, let's see here what happens. K is equal to 1, before I have set 1. Sorry, before doing the poles, let's write the integral. Is the integral over 1k, b chi. Okay? Now, what is this? I different from j, therefore this does not exist. This is product from I and j. I is just 1, therefore this gives x over epsilon 1, epsilon 2. Okay? And then from here, I have product over u from 1 to n, 1 over chi minus au plus epsilon over t, and chi minus au, sorry, iu minus chi plus epsilon. Okay. Okay, I should look for the poles in the upper half plane, therefore I should just switch to this. Okay. Therefore, this is what? You have epsilon over epsilon 1, epsilon 2. And then I will hit here, let's say for example, I hit here, then I have some over u. You see, I have u from 1 to n. For every u, I have a pole. Okay? For a 1, a 2, a 3, and so on. Let's take the u of S1. I take the pole, this pole will give me minus sign here. Okay? When I take the residue of this, and then from the u part here, I will get epsilon over 2. And then I have the product from v different from u of this quantity. And here I already can write instead of chi, I can write au plus epsilon. So this is the product au minus av. This is av plus au. Okay? And you see already that what I was telling, okay, you see already two things. First, that is true, that there is one pole for each Young tableau, because I can put the Young tableau here, or here, or here. All the contributions are coming from the different points where I put them. Okay? You see also that this goes like 1 over epsilon 1, epsilon 2. Okay? Therefore, sorry, I didn't say you, but this K was from 0 to infinity, and I defined set of 1, set of 0 like this. Okay? Therefore, let's compute the prepotential. The prepotential will be F will be minus epsilon 1, epsilon 2, limit when epsilon 1 goes to epsilon 1 and epsilon 2 goes to 0 of log of 1 plus Z1 times Q. Okay? Log of 1 plus Z1 is minus Z1, so this is epsilon 1, epsilon 2, Z1. Q. Okay? Then I plot this and this again. 1. The 1 over epsilon 1 is from 2 cancel. You have minus this factor 2. Okay? And then I have here sum u equal to 1 when 1 over a u v. This is, I can put the minus here outside. And write this AUV squared minus epsilon squared over 4. And this will be minus the number of terms in this product, minus 1. Minus 1. Okay? Then this is the answer. You see it's finite. This is F. This F starts like that. And then, of course, now we should compute K squared and so on. This is the first. Depend on A. Sorry, and now it's on to epsilon to 0. Therefore, this is just 1 over sum over U, 1 over. Therefore, we learned that the F F is sum over k, Fk q to the k, and the first coefficient, F1, is simply 2, sum 1 over 2 is minus 1 to the n. There's these 2, and then A will be product. Here there was a product over V. Product, sum over u from 1 to n. So product over V equal to u, 1 over u. It's clear? Questions? What can this?
It's almost
Almost 15, still I have for half an hour.
Yeah.
Okay. Okay, this is F1. Now we should decide here what to do. We can do either F2 explicitly, or we can try to do the Seiberg-Witten curve. I think it would be more. Maybe I will just say you for F2 what are the main contributions, and then I will go to the Seiberg-Witten curve. Of course, this would be very quick, but at least to give you an idea what is the. Sorry, I can say this is really better.
Just a curiosity. You assume there that all the eigenvalue of the pattern are different. There are problems if some of them collapse. Let's say A1 equal A2.
Yes, this is a very good point. This is very good. One, when two of them collide, there is an enhancement of the symmetry. Yes, and then all this is singular. This is just signing the fact that there is massless states.
There are some problems.
You are, yes, there is a problem. Essentially, what this is a very interesting question: how to make, how to study enhancement of the case symmetry points of the kind in some way. It could be that there is a limit in which you can set, for example, the n equal 4. We expect in n equal 4 that you could set everything to 0 and still recover some final answer. But you should play with something. This cannot be simply said just together.
Because in some sense you are near, I mean, the limit is going to a border of some geometrical structure related in the classical theory of post-on foliation.
Yes.
There are always problems when they
I completely agree. Moreover, this is a very famous computation by Giancarlo Rossi, Veneziano. There are two groups essentially who can do instanton. Before all these computations were done with this localization and all these techniques, the people do exactly, they study directly the instanton and the instanton for SUN, all the values with touch to see. And the fun thing is that if you compute just directly, you start from this integral for k equal, even for k equal to 1, k equal to 1, the only case they know how to do, they compute the partition function, put all together, and they find a number. Then you do with the rest, compute the partition, and you find and then you find a different number. And no, still is not understood why these two computations don't give the same answer. Therefore, it's saying that what you are saying, there is some singularity there, and this we still don't understand. Therefore, this is a prescription. When I say I'm computing the prepotential for SUN gauge series, I really mean theories that are broken to U1 to Vn, and then but are not really.
in the geometry there is a collapse of dimensions.
Yeah. It's open up a different, completely new branch, and therefore you should take into account more. You cannot do so life. I think this is a very interesting point to. Therefore, all computations I will present will have this point. Will be always ratios where the difference of the 8s will come in the, every time you have an enhancement of the symmetry, there will be some singularity. Okay, let me just say that if you do this this for k equal to 2, essentially, what you will find something like then you will find Q set of a box plus Q squared set of a box, 2 box plus set of 2 box minus 1/2 set squared. You see, it's a log. I'm expanding the log. The log will have one contribution from Q at order k equal to 1. Then you will have the joint log at order 2. But then the expansion of the log gives us subtract 1/2 set of the z1 squared. And this quantity, if you just compute this, you will see that this will start like 1 over epsilon 1 squared, epsilon 2 squared. Which is what we were saying, set was starting, zk will always start with 1 epsilon 1, epsilon 2 to the k. It's a very bad singularity. You go higher in k and z is going worse and worse. Okay? But once you compute the log, the terms 1 over epsilon 1, epsilon 2 squared from here cancel with the square of z. Essentially, it's like a disconnect. You are taking what we are saying is that the log, which is the connect part, is much better than the disconnect. All these singularities are just the square of a singularity you already. It's just the fact that you have a disconnect now. Then the log is a very nice function, which is completely finite, and you can compute by simply computing the residues of this integral. Okay. Okay, what I will do now is called the Seiberg-Witten techniques. This was really discovered before all this instanton business, before localization. And the idea is that they discovered that if you want to compute this prepotential is a holomorphic function, and it's very restricted by the physics of the problem. For example, you know where this function have some log singularities because some massless part is coming to 0 and so on. But you have several constraints on this end. And what they found is that they can write this. There is a single function f that satisfies all the mathematical requirements. And they say, okay, the probability should be this, just from the symmetries. They write a curve that codifies the prepotential completely. You take this curve and you can extract all the numbers, or these numbers I compute here, you can extract them from a nice geometry. Okay? I will do here the opposite way around. What I will do here is, starting from this, I will show you how the curve emerges. Now you say, okay, but why I care? I can do the computation for k equal to 1, 2, and 3, but okay, you can imagine that this interval becomes more complicated and so on. Therefore, knowing, you see, the computation that we are doing is much more complicated than we really need. We are computing this quantity that depends on epsilon 1, epsilon 2. Okay? But we don't want that. At the end, we compute a very big object and then take the limit epsilon 1 to go to epsilon 2. Then what I will do now is show you that if you send epsilon 1 to epsilon 2 to 0, before computing this, just keeping this, sending epsilon 1, epsilon 2, I will do the following. I will take this product and write in this form. I will show you that you can the limit epsilon 1 goes to epsilon 2 to 0 is very simple. simplify out this computation. We did here in the opposite way around. We compute the integral and then do the limit. I will do here, I do the limit and then compute the integral. Okay? Now we have zk is an integral over chi k of some function zk of chi k, which is this problem, this big problem. What I will do is just write integral of kk exponential to the log zk. I have not done this. Okay? And then I take the limit. Epsilon 1 goes to epsilon 2, goes to 0. And we will see that when epsilon goes to 0, okay, this integral becomes e to the, sorry, let me write it this way. Sorry, close. Or no, let me keep it like that. Let me call this log, let me call it this way. 1 over epsilon 1, epsilon 2. I will see that in this limit, epsilon L goes to 0, this goes to some 0. What I will show you is that now I take this exponential. Okay? You almost see already here, no? Because, okay, no, you see, okay, let's what I will show you is that from epsilon 1 to 0, this goes like this. Okay? Just expand this. And then, this is nice because if I want to send epsilon 1 epsilon 2 to 0, you see this is exponentially surprised. Therefore, the only contribution will come when this is a minimum. And what I will want to show you is that this is exactly the Seiberg-Witten. So, what we want to prove is that in the limit epsilon 1 equals to 0, which gives me the case 0, all these integrals simplify and become a simple curve. And from this curve, I can extract f1, f2, f3, and so on. Now this curve contains all the instanton collection. You could even evaluate a strong copy and extract the strong copies without knowing what is. It's easier to extract the last coefficient than the third. Okay. Okay, the idea is very simple, no? I just exponentiate that. You see the log, this will be exponential log. All this sum will become, all this product becomes sums. Then I will have these sums, k is any number. This will be very large, therefore all these sums will become integrals. And then this will become a functional. And this will be a functional, and then this will be an equation for these guys. Okay, this is the idea. Now let's do it. Okay, what is HK? HK is equal. I put one epsilon 1 epsilon 2 here, therefore I should put epsilon 1 epsilon 2 here. And then log of this, no? This becomes sum. Let me write and then explain each one. I introduce a function p, ps, which is just a product u goes to 1 to n of x minus n. Now, what is this? This is the log. I do exponential of the log of this. The log of the product is the sum. And then here you have log of chi ij plus epsilon, chi ij plus epsilon 1, chi ij plus epsilon 2. Here I should just remind that this is I different from j for the first term. This is minus p. P is this part. Log of this product, this is a p, x minus au, where x will be chi I plus epsilon half, and the other is x minus epsilon. Okay? Then I just take the exponentials. Good. Now, what is chi? Chi is a function. We already see how it looks like. Chi is some distribution of, they will be like the Jota blocks, no? They will be, I don't know, in 1, 2, and 3, they will be concentrated around the various vectors. Okay? Therefore, I will write for chi this expression. I will introduce this density. Then, how can I write this? Sorry, no. Before I wanted to expand this. Okay, let's expand this. You want to take epsilon very small. Here you can do. See, okay. But here you see, if I write this like log of, I divide by chi ij everywhere. Therefore, I have here chi ij. Okay, let's expand this. If I expand this in epsilon 1, epsilon 2, you see the first term cancel. This will be 1 chi ij plus. Then you will find a term from here, epsilon over chi ij minus epsilon 1 over chi ij minus epsilon 2 over chi ij. No, this was coming from here, and these two minus coming from here. Okay. Plus, then the next one will be the first non-trivial one. Therefore, the first non-trivial one will be, and if you do this computation, you will see that the first non-trivial will be epsilon 1, epsilon 2, chi ij squared. Okay? Therefore, all this part I can replace this by all this this log. I can replace log of 1 plus that 1, this is 0. Log of 1 plus something small is just that. Okay? Therefore, I can replace all this log. Let's put the x1 is going to inside by. Sorry, it's better maybe. Okay, I will calculate just if you want. Maybe don't cancel. Okay, then we are saying that hk is equal to the first term, there was x1 something. The first term will be minus epsilon 1 squared, epsilon 2 squared, sum over ij 1 over ij squared. Okay. While the second term was 2 epsilon 1 epsilon 2 log p. Okay. Okay, now I introduce this density. You see, this is something that is non-zero every time there is an instant. Therefore, this rho simply send me where the instanton are. Okay? And I simply, you see, I can rewrite this equation, this sum over I and j. Using this, I can write as an integral over dx dy rho x rho y over x minus y squared. You just plot this here, no? This will be integral dx dy sum I and j delta x minus I delta x minus j x minus y squared. And now you do the integral. The integral will simply say that x and y is xi xy, and you get the final. And then you have the x and y squared. But you see that these two things are the same. I'm just rewriting this. I'm just rewriting a sum as an integral. Okay, this is the first term. What about the second term? The second term I can also rewrite minus 2 every time I have a sum over I. Epsilon 1, epsilon 2, sum over I of something that you cannot cut, I simply replace it by the integral of dx rho x and the log of p. Okay. And then the last term is the same, log q integral x. Okay, but then I convert all my h now is a function of rho. Rho, if you give me rho, I know where the instantons are. Therefore, rho is just the density of it. It's just a function that codifies all the position of things. All this John tableau business are inside rho. Choosing rho is choosing one John tableau. You have infinite choices because you have infinite number of John tables. Okay? But since we want epsilon 1 goes to 0, we should experiment this function. Therefore, we should see for which rho this integral is an infinite. Okay? Therefore, what is the variation of h? The variation of h should be 0. I just take the variation of this function with respect to rho. Here I will have factor integral of a rho. Let's say I take a variation. This is dy of y x plus y squared. And then the variation here of rho is simply 2 minus 2 log dx. The variation here is this. Okay, therefore we see, and where this should be, it should be in all this region, in some region, this will be, of course, if rho is 0, if rho is away from the instanton, this will be automatically satisfied. Therefore, this will be non-trivial only in some intervals, sigma u, where rho is non-zero, along you have all your expectation values, 1, 2, 3, and so on. Around here, the instantons are there. Here, all the instantons distributed around this ace. Okay. Therefore, this sigma 1, this is sigma 1, sigma 2, sigma 3, sigma 4, and so on. There will be some settlements where what I'm looking for is a density rho such that it satisfies this equation in some finite number of sentences, centered exactly at the position of A. Good. Okay. Then let me define now, we're almost done. We already have the equation. Let me define now this object. It's roughly the exponential of this. Exponential of this of 2 log of, sorry, exponential of 2 into the dy from y over x minus y squared minus 2 log x. Sorry, without the 2. Let me define this out. This y is, sorry, it's not the same as this y, it's called this. This is just a change of variable. Instead of work with rho, I prefer to work with this y.
Can we call it something else?
I can call everything else, but I don't want, because y is used for the Seiberg-Witten. You will see now that you will be very happy that this is called y. Okay, this is, I call y, this. And I say again, this is just half the information of rho. It's just I don't want to work of rho, I want to work. Another thing is, again, here there is a problem. I should say how I do this integral, because there is a 0 here. Let me put plus I 0 plus. I define y in this way. Just a small imaginary part to show you that this makes sense. Okay, but then what is this equation? This equation is simply, see, if I take the exponential of this equation, it's just modulus square of y is equal to q. You just take the exponential of this. The modulus square is the 2. And then the exponential of q is, okay, then there is a sign. I take the opposite sign here. You see that in the one variables, the equation is very simple. It's just modulus square of y is equal to q. Another thing you see, for example, when x goes to infinity, x also notice that when x goes to infinity, this was a polynomial of order n. Therefore, when x goes to infinity, y goes like exponentially to the log of x to the n. Okay? Which is roughly like x to the n. And then yes, I make the error from something. This is minus x to the minus. Okay, then I keep these signs, then maybe this sign, okay, the sign will check there later, to such a way. So, okay, what I want is also that I have an equation for y, which is very simple. Y squared is equal to q. And I have a boundary condition that say that when x goes to infinity, y goes this way. Okay, this is enough. Because then you can write, for example, y, x writes also to satisfy this problem. It's imaginary, the model, the complex module is q, and this goes like x to the n. I take a polynomial for the n, okay, and I take, let's say, 1/2 minus the square root of pnx squared minus 4. Now, this polynomial, this function satisfies all these problems. First, the first thing is that it's imaginary every time you are close to some of the poles of this polynomial. For this polynomial is not the same as p. I call Pn now. It's a different polynomial. Px plus prom of u goes to 1 to n of x minus AU. This Pnx product of U goes to 1 over n, x minus, I don't know, let's call it EU. A different, I don't know. Here, the only thing I know is that this is a polynomial for the n. I don't know which polynomial. I cannot say that this is the same P of n. Okay? But these have this property. You see, when y with x is very large, this cancels with that, and this goes like 1 over x to the n. If I take the modulus square, or if I am in the region where this is imaginary, okay, the modulus square of that is just this times the same with the plus, which means p squared minus p squared cancel, plus 4q, okay, over 4, which means q. Therefore, this satisfies this condition in all these regions where this quantity is smaller than 4q. See, every time that p squared n is smaller than 4q, and this will happen n times, because this is a polynomial for the n, this will satisfy this condition, and it's a very condition of infinity. This is what is called Seiberg-Witten. For UN. You can repeat the same for any group with matter, with other gauge groups and things like that. And the analysis, if you know the microscopic derivation of this instanton computation, the analysis is this. Okay, but the funny thing, I think you will study a lot of this Seiberg-Witten curve with Stefano Cremonese the next week. Cool? Okay? Therefore, now you see the microscopic derivation. He will not, he will present from all the implications of this curve. But it's nice that you know how to derive this from first, just through integration with the whole space of Instantons. And then now it's clear that with this y you can compute everything, because knowing y you know rho, then you can compute the prepotential. You see this is a curve, this is a funny geometry. This is a geometry. All this you will see in detail, therefore I don't have to spend time, but just to say this is a geometry that this is a polynomial of order 2n, and there is a branch plot. Therefore you have 2n points, all the zeros of this guy. No? So let's say you are doing S3. You have 6 points. This is 2, 4, 6, 8, 10, 12. This is 6. You're doing S6, you will have 12 points. Yeah. Okay? And then you can compute everything. You will compute all the, for example, all the quantities, the prepotential, you will compute like computing periods of a form construct out of this y along these branch points. Here you can compute the integral around here or the integral around here and so on. This will qualify completely the theory. You will have 2n quantities, n of them is the vacuum expectation value. Here you have 2n periods, n of them will be related to these a's. We compute what is a in terms of this EU. And the other n, in other words, you will see a formula like this. Let me just give you the formula such a way that you can even, let me see this one. But you will study a lot. O AU and derivative of the prepotential with respect to AU Okay, this is what I were doing. If you have a geometry like that, there are two types of cycles. There are cycles that go like this sigma 1, sigma 2, okay? And there are cycles that connect the two. We call this sigma 1 tilde, sigma 2 tilde, and so on. These points were the zeros of this square root. Okay? And then what you should, then you define this lambda is just the derivative of the log of y. Okay? This is a one form. And then the one form you can integrate over one cycle, either of the one time, either of the second time. Integrating over one time, you will compute AU as a function of AU. And this, you will compute the prepotential as a function of. Of course, you can invert this and write AU in terms of AU, and then you will have the prepotential. And you can check, you see in the notes, I did explicitly k equal to 2 for SU2, and you can compare the two computations. I did both in the necklace of language, both for the Seiberg-Witten, and you can see that the results exist. So this is a very, very nice geometry, and you will study a lot, and there are people that do Seiberg-Witten for the whole life, because it's really very rich subject. Or you can, and now you have the derivation of this result. And you can do more, because you see, this is just the epsilon 1, epsilon 2 limit of this huge object. But now we are now starting to learn that also going away from this limit, you find a lot of interest in this limit. And there are already a lot of results in which you can do the same as did here, for example, the same saddle point computation. You can do if you keep one of the epsilon, and you find a sort of quantum deformation of the Seiberg-Witten curve. It's very funny. It's like having a Seiberg-Witten curve in a non-commutative space. I mean, there are a lot of developments you can think about. Okay, this is the end of the course. I thank you for your patience. I will be here till tomorrow, let's say 11 or less.